Well, I can pretty safely say that no one expected this. Google is announcing Project Suncatcher. Now, in the Bay Area, you hear the term moonshot quite a bit. Don't ever take it literally until now, because this moonshot project, Suncatcher, well, it's literally putting AI data centers in space. Here's the Google announcement. They're saying exploring a space-based scalable AI infrastructure system design. And this isn't some pipe dream or far, far away project. According to the demos they did, it's surprisingly realistic. And the first sort of prototype is going to space surprisingly soon. Project Suncatcher is a moonshot. Let's see who wrote this. Travis Beals. He should get a raise just for writing that. So Project Suncatcher is a moonshot exploring a new frontier, equipping solar-powered satellite constellations with TPUs and free space optical links to one-day scale machine learning compute in space. So you get what they're saying here. They're going to have these satellites. They're solar-powered satellites. So they're going to capture the energy from the sun, right? Sun catchers. And on board, they're going to have TPUs. What are TPUs? Those are the AI chips that Google uses, right? So NVIDIA is GPUs. So a GPU is a graphics processing unit. Google's TPUs are Tensor Processing Units. They're AI chips. This is what allows us to train AI models, to run inference on the AI models. So Google has their own TPUs, NVIDIA has their own GPUs, and there's some other ones that are being developed right now as well. These things need massive amounts of power. In fact, a lot of people are concerned about the sheer amount of electricity that these data centers consume. Electricity is not free, and there's only so much capacity that we have. If there was only something out there that could produce massive amounts of electricity, that would be free. Like, for example, the sun. Okay, so that's solar-powered satellite constellations. Constellation meaning that there's a lot of them. And as you'll see, they kind of have to fly in formation. They're not just like flying in all different directions. They have to stay in a certain formation. Why do they have to stay in formation? Well, it's because of this part, free space optical links. What are free space optical links? They are, I don't know why they didn't use this terminology, they're freaking space lasers. One important thing about these AI data centers is that the transfer between the various AI chips, between the processing units, they has to be fast. There has to be massive bandwidth. So just to give you an idea, the NVIDIA's Blackwell systems has a massive transfer speed. So the peak global internet traffic was recorded at about 25 terabits per second. This Blackwell system is 130 terabits per second. So it's many times faster than this single moment peak that the entire internet achieved. So it has to be able to transfer a lot of data. So these, what do they call them? These free space optical links, again, space lasers. They have a high bandwidth communication between the satellites because, well, they're in space. They're in a vacuum. In the paper they publish, they talk about kind of like what kind of speeds they will need and how they can be achieved. One notable problem is that the bandwidth, the total speed of the transfer, really drops off with distance. The further these satellites are, the slower they can transfer data between them. That's why they have to fly in that very precise formation. By the way, they did a bench scale demonstration, so just kind of a feasibility demonstration of this technology. And here they found that using off-the-shelf components, so they don't have to manufacture some specialized equipment, using off-the-shelf components, they did achieve their needed bandwidth, again, validating the potential of this approach. So space lasers, check. Well, you might be wondering, this is Earth, by the way, so why not just put it on Earth somewhere, right? I mean, the sun's rays certainly reach the Earth. Why can't we just take some piece of unused land and just put both of these things there? Well, there's a couple of reasons. One, if you have these satellites in space, you pick up a lot more of the energy. If you're on the ground, the sun's rays, first of all, bounce off the atmosphere. There's humidity, there's clouds, there's all sorts of stuff that prevent it from reaching the Earth. Plus, and this might come as a surprise to some of you, like for half of the time, it's like nighttime. This is true, I've checked. Do you know where sun shines all the time? In space. Well, specifically in one place. It's a Dawn-Dusk Sun-Synchronous low Earth orbit. So if this satellite constellation is staying in this Dawn-Dusk Sun-Synchronous low Earth orbit, you'll be getting almost near constant sunlight. Now, why is this a big deal? I mean, obviously it's efficient, but this reduces the need for heavy onboard batteries. It's expensive to send stuff to space, and the heavier it is, the more expensive it is to send it to space, and the batteries are heavy. Not needing batteries or reducing the reliance on batteries greatly decreases how expensive this project will be. All right, so what are the key challenges here? How realistic is this thing? Well, these large-scale machine learning workloads need to distribute tasks across numerous accelerators with high bandwidth, low latency connections, meaning that there's got to be a lot of connections between these satellites, and they have to transfer information super, super fast. To be comparable to Earth-based data centers like the ones that we're building here on Earth, the ones that are supporting Gemini and AlphaFold and all the other AI models, Well, they need a certain bandwidth, a certain speed. And we talk about this. They demonstrated that they likely can achieve that in space. Again, there's that whole idea that the farther apart the satellites are, the slower they are. So they have to be pretty close. These satellites have to fly in very close formation, kilometers or less. But this is looking like it's viable. How do we control all these satellites flying in close formations? Well, they created a physics model to see how possible this is. They used 81 satellite constellation configuration in the orbital plane. The cluster radius is 1 kilometer, with the distance between the next nearest neighbor satellites oscillating between 100 to 200 meters. And what they were able to show that with these satellites positioned just hundreds of meters apart, they will likely only require modest station-keeping maneuvers to maintain stable constellations within our desired Sun-Synchronous orbit. When Google announced AlphaEvolve, so how they've sort of used the Gemini models to come up with some discoveries in the realms of mathematics, hardware design, they used it to optimize some of their data centers. Like they showed how these large language models could sort of optimize a lot of these processes, come up with some even pretty new novel discoveries. One thing that I noticed is the results that they published were of a somewhat outdated model from about a year prior to them publishing the paper. I was very curious to know what else these AI models are cooking up in the background. And sometime later, Google releases this. We're going to build freaking AI data centers in space, swarms of satellites keeping these stable formations, always pointing towards the sun, talking to each other through space lasers. I'm sure it's a total coincidence. Let's move on. Now, the next big challenge, of course, is that these TPUs, these fairly sensitive chips, aren't they just going to get cooked with radiation in space? So here they're measuring kind of the total absorbed radiation in these standard units. So basically the most sensitive components on board, they start starting to mess up and have errors at this dose, at a cumulative dose of 2 Krad. So 2,000 rads, which is nearly 3 times the expected 5-year mission dose of 750 rads. Right, so if we're putting that thing up there for 5 years, we expect it to soak up 750 units, and it doesn't start tripping until 2,000 units, which is awesome. Again, this seems doable. One interesting thing that they say here is that the TPUs are surprisingly radiation hard for space applications. So they cranked it up to 15K rads, so 15,000, and noticed no hard failures. So what does this all mean? Well, this means that AI plus space is good. AI plus space is good. The only question is, as always, is it going to cost too much money? How feasible is this? I mean, at this point, they're saying that it's realistic, right? It could work. These TPUs are very resilient. Space lasers can transfer enough power. We can keep these satellites baking in the sun rays 24/7. I mean, this sounds almost too good to be true. Next, they're going to tell us it's cheaper to build everything in space. Is that true? Well, not quite, but there's some things to understand about that. I'll link the paper down below if somebody wants to go through this math, but I'll kind of just simplify it here. You can think of the cost of energy as some amount of dollars per kilowatt per year. So imagine you build a power plant here on Earth. So at this point, you're able to generate electricity at about 810 per kilowatt per year. So it's important to understand that this is kind of annualized. So it's like the total amount of money you spent on everything, kind of calculated out, to get everything that you need, the output, the kind of cost per unit is this, right? So what if instead of putting all that money into a power plant, we put that money into this satellites in orbit? At what point will this cost the same as a terrestrial power plant per unit of electricity? Well, really what that comes down to is this. It's dollars per kilogram of basically how much it costs to send stuff to a low Earth orbit. So the cheaper that we can send stuff to space, the more economically feasible it is, because then at some point we can produce energy for cheaper per unit than on Earth. I hope that makes sense. So what is this dollars per kilos? What does that price need to be for it to be equivalent to how much it would cost to produce it on Earth? That number is $200 per kilogram. $200 per kilogram, that's kind of the break-even point. At $200 per kilogram, it's the same cost as building it here on Earth. Although I feel like at that point, you'd elect to build it in space because there's probably tons of stuff here on Earth, ongoing costs, etc., that just don't exist up there. Meaning that it would probably make sense to build everything on space, even if this price was higher. But the higher it goes, the worse it gets. It sounds like even at $300 per kilogram, it would still kind of make sense. Like the per unit price of electricity would be just under double what you could get on Earth, but it still might be feasible. So the big question is, if it's $200 per kilogram is kind of what we're shooting for, where are we now? Well, a lot higher, let's say. Current ranges are from $1,500 per kilogram up to $20,000 per kilogram. Now, before you get too depressed, here are the good news. There's a number of these industries where we're seeing a high and sustained learning rate. The Google paper, for example, specifically points to solar panels and that industry, the sustained learning rate and expansion of that industry. Progress can seem slow at first, but once it gets going, it really blows up. Assuming a continuous learning rate, the improvements in technologies, the improvements in manufacturing, etc., progress continues maybe slowly at first, but then there's a certain threshold at which it just makes all the sense in the world. The costs are down, the availability is up. It makes almost no sense not to pursue it. It really unlocks a lot of the usability. We saw perhaps a similar thing happening with electric cars. So we are seeing a certain acceleration in some of these industries like solar panels, electric cars, and rockets. We're hoping that the growth in rockets will be as good as solar panel and electric vehicles. So coming back to the Google paper, here they're saying SpaceX launch pricing data and mass launched from Falcon 1 to Falcon Heavy yields a 20% learning rate, meaning that the price per kg falls by 20% for every doubling of cumulative mass launched. So if there's one sentence in this report that I think truly encapsulates whether this thing is happening or not, at least as far as I can tell, because everything else seems like it's feasible, it checks out. We just need to get this dollar per kg number to less than $200. Elon Musk, of course, owns SpaceX, his aerospace company, as well as Tesla, his electric vehicle company, as well as Twitter and Neuralink. He also owns a SolarCity, the solar panel company. And that's why I think this sentence is so important, because a lot of the numbers and models and projections are based on the results that SpaceX has achieved. They're saying if the learning rate is sustained, which would require around 180 Starships launches per year, then we expect the launch prices to fall to less than $200 per kilogram by around 2035. Now, that is not to say that there are not other companies, whether they are in the US or elsewhere, that are also doing this space race and developing amazing technologies that might get us to that point eventually. But this projection is based on the results of SpaceX and this whole thing becoming viable by around 2035. That's based on Elon and friends continuing to do what they do. If we want swarms of AI data centers in space communicating to each other with freaking space lasers, here's a paper by Google basically saying, hey, we figured everything else out. We just need Elon to keep cranking out rockets and continue his learning rate like it was. As they continue here, while this would be a substantial achievement for SpaceX, meaning getting it to this price per kilo, it is still far below stated launch targets for Starship. Even if this launch rate is reduced by 70%, prices could drop to $300 per kilo in the same time frame, which would still have a substantial impact on feasibility of these large-scale constellations. And this is why, Google's going to be around in 100 years. They're saying, given the long lead times required to reach scale for this type of ambitious project, it's strategically beneficial to commence work on early milestones in anticipation of projected price declines. So in summary, we have pretty much everything we need to launch this thing to space. The last thing that we need, and maybe or probably, depending on how you view it, if we project forward, we believe that the economic feasibility will reach the number it needs to reach by mid-2030s, because at that price point, the cost of launching and operating a space-based data center could become roughly comparable to the energy cost of running it on Earth. Now, obviously, there's some other significant engineering challenges, but the point is, it seems feasible. It could significantly improve energy production. A lot of stuff we need energy for doesn't necessarily have to be here on Earth. And Google is launching their first prototype, prototype in space by early 2027. They're partnering with Planet and launching 2 prototype satellites. This will test how the models and TPU hardware operate in space, validate the use of optical inter-satellite links space lasers for various distributed ML tasks. And really, this is the interesting part. When we build this stuff in space, if you think about it, pretty much everything, all our technology, everything was invented and optimized and improved. It was made with sort of one lens, from one sort of lens that we were looking at it through. It had to work on Earth. Like any of our factories and energy production facilities and research labs, they weren't made by asking, what's the best way of doing this? It was made with, what's the best way of doing this in the context of that it's going to be placed somewhere, on the Earth's surface or somewhere in an atmosphere on Earth and all the limitations that went with it. Nowhere on Earth do you get 24/7 sunlight that's not diffused or somehow blocked by the atmosphere and clouds and humidity. Creating large-scale vacuums is difficult. Often when we have a motivation to figure stuff out, it's driven by some new breakthrough or device. Here they list, for example, the modern smartphones. Right, the development of complex system-on-chip technology was motivated by and enabled by modern smartphones. Building stuff in space not only will solve a lot of our current problems, but very likely will also enable a whole host of new solutions and insights that we haven't had before. Interestingly, one name jumped out at me in the acknowledgements section. That is Blaise Aguirre y Arcus. He was, of course, on the machine learning podcast recently. I did a quick video kind of covering some of the things that I found the most fascinating. I was completely blown away by some of the stuff he was talking about. I kind of speculated what they're working on in Google, and boy, was I off. Nowhere near. It seems like they're working on their space-based, highly scalable AI infrastructure with space lasers. But I was right about one thing, and that is you're going to be hearing his name again. And there it is, of course. Congratulations to all the people that have worked on this and published this. I'm sure we are all extremely excited to see where this goes next. Hopefully, SpaceX and Google will continue their learning rates and make sure that we're able to get these things in low Earth orbit for under $200 a kilo by mid-2030s, or at least around there. I hope that's not too much of an ambitious goal for Elon Musk, that he's not too intimidated by it. A few days ago, Elon Musk posted, "Perhaps our purpose is to make the mind of a sentient sun." Yeah, I think we'll be fine. The future is bright. My name is Wes Roth. I'll see you in the next one. All puns intended.